While specific municipal requirements for NEMA TP-1 Energy Star ratings on distribution transformers may be uncommon, broader energy efficiency policies and incentives often encourage their use. State and local energy codes in some areas include requirements for energy-efficient transformers in specific applications. Many utilities provide incentives or rebates for customers who install energy-efficient equipment, including transformers. In California, the California Energy Commission has established the California Energy Efficiency Regulations, which address energy-efficient distribution transformers. In New York, the New York State Energy Research and Development Authority, or NYSERDA, provides incentives for energy-efficient equipment, including transformers, through its NYBEST program. In Massachusetts, the Massachusetts Clean Energy Center offers rebates for energy-efficient transformers through their Transformer Rebate Program. The Oregon Department of Energy offers incentives for energy-efficient equipment, including transformers, through the Energy Trust of Oregon programs. Local building inspectors may review electrical plans during the building permit review process to ensure compliance with applicable energy codes or ordinances, potentially including requirements for energy-efficient transformers. Furthermore, owners or developers might choose to specify NEMA TP-1 Energy Star rated transformers on a project-by-project basis to achieve sustainability goals or lower operating costs. It is always best to check with local building departments, utilities, and other relevant agencies to obtain the most current details regarding energy efficiency requirements and incentives. In considering transformer efficiency, it's useful to understand some key aspects of their operation and the standards that govern them. The National Electrical Manufacturers Association, or NEMA, has set standards like TP-1 to define minimum energy performance for distribution transformers. Energy Star is a program run by the U.S. Environmental Protection Agency, or EPA, that promotes energy-efficient products. Distribution transformers are essential components in electrical power distribution systems, stepping down voltage from higher transmission levels to low levels suitable for use in homes and businesses. These transformers consume energy even when not fully loaded, so efficiency is crucial. Transformer efficiency is the ratio of output power to input power, usually expressed as a percentage. Higher efficiency means less energy is wasted as heat. NEMA TP-1 standards specify the minimum efficiency levels for distribution transformers at specific load levels. These standards help reduce energy consumption and lower operating costs over the transformer's lifespan. When evaluating a transformer's compliance with NEMA TP-1, you're looking for a transformer that meets or exceeds the minimum efficiency requirements outlined in the standard. Energy Star rated transformers are certified to meet specific energy efficiency criteria set by the EPA. These criteria often align with or exceed NEMA TP-1 standards. Transformer losses consist of two main types. Firstly, core losses, which are constant losses that occur in the transformer's core due to magnetization and demagnetization. Secondly, copper losses, also known as load losses, which vary with the square of the load current and occur in the windings due to resistance. To improve transformer efficiency, manufacturers use several techniques, including firstly, using high-quality core materials with low hysteresis and eddy current losses. Secondly, optimizing core design to reduce magnetic flux leakage. Thirdly, using larger conductors in the windings to reduce resistance and copper losses. Fourthly, improving insulation materials to reduce dielectric losses. The benefits of using energy-efficient transformers are numerous. Firstly, reduced energy consumption, leading to lower electricity bills. Secondly, lower greenhouse gas emissions due to reduced power generation requirements. Thirdly, extended transformer lifespan due to reduced heat generation. Fourthly, potential eligibility for utility rebates and incentives. When selecting a transformer, consider the load requirements, operating conditions, and the cost of energy over the transformer's lifespan. A higher efficiency transformer may have a higher initial cost, but it can result in significant savings over time. Also, consider the environmental benefits of using energy-efficient transformers, such as reduced carbon footprint and conservation of natural resources. When installing transformers, ensure proper ventilation to prevent overheating, which can reduce efficiency and lifespan. Follow manufacturers' recommendations for installation and maintenance. Regularly inspect transformers for signs of damage or overheating. In some cases, municipalities may have specific requirements for transformer efficiency in new construction or renovation projects. These requirements may be part of the local building code or energy efficiency standards. Check with the local building department or energy office for specific information. Some utilities offer rebates or incentives for customers who install energy-efficient transformers. Check with your local utility for available programs. The Database of State Incentives for Renewables and Efficiency, or DSIRE, is a comprehensive source of information on state, local, utility, and federal incentives and policies that support renewable energy and energy efficiency. It is important to note that the specific requirements and incentives for energy-efficient transformers can vary significantly depending on the location and application. Always consult with local authorities and utilities for the most up-to-date information. Understanding transformer efficiency standards and the available incentives can help you make informed decisions when selecting and installing transformers. By choosing energy-efficient transformers, you can reduce energy consumption, lower operating costs, and contribute to a more sustainable future. Now, let's discuss specific considerations for different types of transformers. Distribution transformers are commonly used to step down voltage from higher distribution levels to lower levels suitable for residential, commercial, and industrial use. These transformers are typically located near the point of use and are designed to operate efficiently at varying load levels. Medium voltage transformers are used in industrial and commercial applications to step down voltage from medium voltage distribution levels to lower levels suitable for equipment operation. These transformers often have higher efficiency requirements than distribution transformers due to their larger size and continuous operation. Dry-type transformers are cooled by natural air convection and are commonly used indoors where liquid-filled transformers are not permitted. These transformers are designed to be energy efficient and safe for indoor use. Liquid-filled transformers are cooled by oil or other dielectric fluid and are typically used outdoors or in substations. These transformers can handle higher loads and are often more efficient than dry-type transformers. When selecting a transformer, consider the specific application and operating conditions. For example, if the transformer will be located indoors, a dry-type transformer may be the best choice. If the transformer will be subjected to high loads, a liquid-filled transformer may be more suitable. The energy efficiency of a transformer is affected by several factors, including firstly, the core material, which should have low hysteresis and eddy current losses. Secondly, the winding material, which should have low resistance. Thirdly, the insulation material, which should have low dielectric losses. Fourthly, the design of the core and windings, which should minimize magnetic flux leakage. To maximize transformer efficiency, consider the following tips. Firstly, choose a transformer that is sized appropriately for the load. An oversized transformer will operate at a lower load factor, which can reduce efficiency. Secondly, ensure that the transformer is properly ventilated to prevent overheating. Thirdly, regularly inspect the transformer for signs of damage or deterioration. Fourthly, consider replacing old, inefficient transformers with new, energy-efficient models. In addition to NEMA TP-1 and Energy Star, other standards and certifications may apply to transformers. The Underwriters Laboratories, or UL, is a safety certification organization that tests and certifies electrical equipment, including transformers. The Institute of Electrical and Electronics Engineers, or IEE, develops standards for electrical and electronic equipment, including transformers. The International Electrotechnical Commission, or IEC, develops international standards for electrical and electronic equipment, including transformers. When selecting a transformer, check for compliance with relevant standards and certifications. This will help ensure that the transformer is safe, reliable, and energy efficient. Keep in mind that the cost of a transformer is only one factor to consider. The total cost of ownership includes the initial cost, the cost of energy losses over the transformer's lifespan, and the cost of maintenance and repairs. A higher efficiency transformer may have a higher initial cost, but it can result in significant savings over time. Therefore, it is crucial to perform a life cycle cost analysis to determine the most cost-effective transformer for a particular application. Also, remember that energy efficiency is not the only factor to consider when selecting a transformer. Other important factors include safety, reliability, and performance. Choose a transformer that meets all of your requirements. Finally, stay informed about the latest developments in transformer technology and efficiency standards. This will help you make informed decisions and select the best transformer for your needs. In summary, while specific municipal requirements for NEMA TP-1 compliance might be limited, many areas have broader energy efficiency policies and incentives that encourage the use of energy-efficient transformers. By understanding these policies and incentives, you can make informed decisions and select transformers that reduce energy consumption, lower operating costs, and contribute to a more sustainable future. The key is to investigate local building codes, utility programs, and relevant agencies for the most current and specific information in your area. Let's delve further into some of the technical aspects that contribute to transformer efficiency. Core materials play a pivotal role. Amorphous steel is often used in high-efficiency transformers due to its low core losses compared to traditional silicon steel. The grain orientation of the steel also affects core losses. Grain-oriented steel is preferred for transformer cores. Winding materials are another critical factor. Copper and aluminum are the most common winding materials. Copper has higher conductivity but is more expensive. Aluminum is lighter and less expensive but has lower conductivity, so larger conductors are needed to achieve the same current carrying capacity. The type of insulation used in a transformer can also affect its efficiency. High-quality insulation materials with low dielectric losses are essential for minimizing energy losses. Transformer design also plays a significant role. The core shape, winding arrangement, and cooling system all affect efficiency. Optimizing these design elements can significantly reduce losses. The load factor is the ratio of average load to peak load over a period of time. Transformers operate most efficiently when they are loaded near their rated capacity. Oversized transformers operate at low load factors, which can reduce efficiency. Harmonics in the electrical system can increase transformer losses. Harmonic filters can be used to reduce harmonics and improve transformer efficiency. Proper ventilation is essential for preventing overheating, which can reduce transformer efficiency and lifespan. Transformers should be installed in well-ventilated areas and should be regularly inspected for signs of overheating. Regular maintenance is also important for maintaining transformer efficiency. This includes inspecting connections, cleaning the transformer, and testing the insulation. When replacing an old transformer, consider the benefits of using a solid-state transformer, or SST. SST are more efficient, smaller, and lighter than traditional transformers. They also offer better voltage regulation and power quality. Understanding these technical aspects can help you make more informed decisions when selecting and installing transformers. By considering all of these factors, you can maximize transformer efficiency and reduce energy consumption. Let's explore some additional factors related to transformer efficiency and regulatory compliance. Transformer manufacturers provide detailed specifications for their products, including efficiency ratings, core losses, copper losses, and impedance. Review these specifications carefully when selecting a transformer. Third-party testing and certification can provide independent verification of transformer efficiency. Look for transformers that have been tested and certified by reputable organizations. Transformer efficiency standards are constantly evolving. Stay informed about the latest updates to NEMA TP-1, Energy Star, and other relevant standards. Government regulations can also affect transformer efficiency requirements. Be aware of any federal, state, or local regulations that apply to transformers in your area. Utility companies often offer rebates and incentives for customers who install energy-efficient transformers. Check with your local utility for available programs. Energy audits can help identify opportunities to improve transformer efficiency. Consider conducting an energy audit of your facility to identify potential energy savings. Demand-side management, or DSM, programs can help reduce peak demand and improve overall energy efficiency. Transformers play a key role in DSM strategies. Power factor correction can improve transformer efficiency by reducing reactive power losses. Capacitors or other power factor correction equipment can be used to improve power factor. Smart grid technologies can help optimize transformer operation and improve efficiency. Smart transformers can monitor load conditions and adjust their voltage and current to improve efficiency. Consider the environmental impact of transformers, including the use of hazardous materials and the potential for oil leaks. Choose environmentally friendly transformers whenever possible. Promote energy efficiency awareness among your employees and customers. Educate them about the benefits of using energy-efficient transformers. By taking these additional factors into consideration, you can further improve transformer efficiency and reduce energy consumption. Remember that energy efficiency is an ongoing process. Continuously monitor and evaluate your transformer performance to identify opportunities for improvement. Let's also discuss how to apply relevant National Electrical Code, or NEC, articles when dealing with transformers. NEC Article 450 covers transformers in general. This article provides requirements for transformer installation, protection, and grounding. NEC Section 450.3 covers transformer overcurrent protection. This section specifies the requirements for protecting transformers from overcurrent conditions. NEC Section 450.9 covers transformer ventilation. This section requires transformers to be installed in well-ventilated areas to prevent overheating. NEC Section 450.11 covers transformer grounding. This section specifies the requirements for grounding transformer cases and enclosures. NEC Section 450.13 covers transformer disconnecting means. This section requires transformers to have a disconnecting means that can be used to energize the transformer. NEC Table 450.3 provides the maximum overcurrent protection for transformers rated 600 volts or less. This table is used to determine the appropriate size of the overcurrent protection device for a transformer. NEC Table 450.3b provides the maximum overcurrent protection for transformers rated over 600 volts. This table is used to determine the appropriate size of the overcurrent protection device for a transformer. NEC Section 310.15 covers ampacity of conductors. This section is used to determine the appropriate size of conductors for transformer installations. NEC Article 250 covers grounding and bonding. This article provides requirements for grounding and bonding electrical systems, including transformer installations. When installing transformers, always follow the requirements of the NEC and other applicable codes and standards. This will help ensure that the installation is safe and compliant. Remember that electrical work should only be performed by qualified personnel. If you are not qualified to perform electrical work, hire a licensed electrician. By understanding and applying the relevant NEC articles, you can ensure that transformer installations are safe and compliant. This is an essential part of ensuring overall electrical safety and efficiency. One example would be NEC Table 450.3, which helps determine the correct overcurrent protection for transformers rated 600 volts or less. This table will provide the maximum rating or setting for the overcurrent device, such as a circuit breaker or fuse, based on the transformer's primary and secondary voltage and current ratings. For example, let's say you have a 480 volts to 120 volt single-phase transformer with a primary current rating of 20.83 amps. According to NEC Table 450.3a, the maximum overcurrent protection for the primary side of the transformer is typically 125% of the rated primary current when using a circuit breaker. In this case, 125% of 20.83 amps is approximately 26 amps. Therefore, you would use a 25 amps with 30 amps circuit breaker to protect the primary side of the transformer. However, it is important to consult the specific requirements of NEC Section 450.3 and any applicable local codes to ensure that the overcurrent protection is properly sized and installed. It is also important to consider the transformer's impedance and other factors when determining the appropriate overcurrent protection. Remember, this is just an example, and the actual overcurrent protection requirements may vary depending on the specific transformer and installation conditions. Always consult with a qualified electrician or engineer to ensure that the overcurrent protection is properly sized and installed. Let's discuss specific aspects of transformer testing and maintenance. Regular testing and maintenance are essential for ensuring the safe and reliable operation of transformers. Insulation resistance testing, also known as mega testing, is used to assess the condition of the transformer's insulation. This test measures the resistance between the transformer windings and ground. A low insulation resistance reading indicates that the insulation is deteriorating and may need to be replaced. Turns ratio testing is used to verify the turns ratio of the transformer windings. This test compares the voltage ratio of the transformer to the specified turns ratio. An incorrect turns ratio indicates that there may be a problem with the transformer windings. Winding resistance testing is used to measure the resistance of the transformer windings. This test can help identify problems such as loose connections or broken conductors. Oil testing is used to assess the condition of the oil and liquid-filled transformers. This test measures the oil's dielectric strength, acidity, and moisture content. Contaminated oil can reduce the transformer's insulation strength and cooling capacity. Dissolved gas analysis, or DGA, is used to detect gases that are dissolved in the transformer oil. These gases can indicate problems such as overheating, arcing, or insulation breakdown. Thermographic surveys can be used to identify hot spots on the transformer. Hot spots can indicate problems such as loose connections or overloaded windings. Visual inspection should be performed regularly to check for signs of damage, such as leaks, cracks, or corrosion. Bushing inspections are used to check the condition of the transformer bushings. Bushings provide insulation and mechanical support for the transformer's high-voltage connections. Load tap changer, or LTC, maintenance is required for transformers with load tap changers. LTC are used to adjust the transformer's voltage under load. Regular maintenance is essential for ensuring the proper operation of the LTC. Regular cleaning of the transformer is important for preventing overheating. Dirt and dust can accumulate on the transformer and reduce its cooling capacity. A transformer maintenance schedule should be developed and followed to ensure that all necessary maintenance tasks are performed on a regular basis. Transformer maintenance records should be kept to track the condition of the transformer and the maintenance tasks that have been performed. These records can be used to identify trends and predict potential problems. By performing regular testing and maintenance, you can ensure that your transformers operate safely and reliably for many years. This is an essential part of any comprehensive electrical maintenance program. One more point to consider is the proper disposal of transformers that are no longer in service. Transformers may contain hazardous materials such as polychlorinated biphenyls or PCBs. PCB are toxic chemicals that can pose a risk to human health and the environment. Transformers containing PCB must be disposed of in accordance with federal, state, and local regulations. Contact a qualified waste disposal company for assistance with disposing of transformers containing PCB. Always handle transformers with care to avoid spills or leaks of hazardous materials. By properly disposing of transformers, you can help protect the environment and human health. This is a critical responsibility for all transformer owners and operators. Let's also address the topic of transformer noise. Transformers can generate noise due to the vibration of the core and windings. This noise can be a nuisance in residential or commercial areas. Several methods can be used to reduce transformer noise, including firstly, using a low-noise transformer design. Secondly, installing vibration isolation pads under the transformer. Thirdly, enclosing the transformer in a soundproof enclosure. Fourthly, locating the transformer away from sensitive areas. Fifthly, using active noise cancellation technology. The level of transformer noise is typically measured in decibels, or dB. Noise regulations may limit the amount of noise that transformers can generate in certain areas. Check with your local authorities for applicable noise regulations. When selecting a transformer, consider the noise level that it generates. Choose a transformer that meets your noise requirements. By taking steps to reduce transformer noise, you can minimize its impact in the surrounding environment. This is an important consideration, especially in noise-sensitive areas. Remember that transformer technology is constantly evolving. Stay informed about the latest advancements in transformer design, materials, and efficiency. This will help you make informed decisions and select the best transformers for your needs. By embracing new technologies, you can improve transformer performance, reduce energy consumption, and lower operating costs. Always prioritize safety when working with transformers. Follow all safety procedures and use appropriate personal protective equipment, or PPE. Electrical work can be dangerous, so it's important to take precautions. If you are not comfortable working with transformers, hire a qualified electrician. By following these guidelines, you can ensure the safe and reliable operation of your transformers. This will help protect your equipment, your employees, and the environment. Let's discuss some additional points related to transformer monitoring and control. Transformer monitoring systems can be used to track various parameters such as voltage, current, temperature, and oil level. These systems can provide early warning of potential problems. Transformer control systems can be used to adjust transformer voltage, tap settings, and cooling fan operation. These systems can help optimize transformer performance and improve efficiency. Supervisory control and data acquisition, or SCADA, systems can be used to remotely monitor and control transformers. SCADA systems are commonly used in large electrical systems. Predictive maintenance techniques can be used to anticipate transformer failures and schedule maintenance accordingly. These techniques can help prevent costly downtime. Smart grid technologies can be used to integrate transformers into the grid and optimize their operation. Smart transformers can communicate with the grid and adjust their voltage and current to improve grid stability. Distributed generation, or DG, can impact transformer operation. Transformers may need to be upgraded to accommodate DG. Microgrids can use transformers to connect to the main grid. Transformers play a critical role in microgrid operation. Renewable energy sources, such as solar and wind, can also impact transformer operation. Transformers may need to be designed to handle the fluctuating output of renewable energy sources. Energy storage systems can be used to improve transformer utilization. Energy storage systems can store energy during periods of low demand and release it during periods of high demand. By implementing these monitoring and control strategies, you can improve transformer performance, reliability, and efficiency. This is an essential part of managing a modern electrical system. Also, consider the impact of transformer failures on your operations. Transformer failures can result in costly downtime and equipment damage. Develop a contingency plan to address potential transformer failures. This plan should include procedures for isolating the failed transformer, restoring power, and repairing or replacing the transformer. Keep spare transformers on hand to minimize downtime in the event of a failure. Conduct regular drills to test your contingency plan. This will help ensure that your employees are prepared to respond to a transformer failure. By having a well-prepared contingency plan, you can minimize the impact of transformer failures on your operations. This is an essential part of risk management. Let's further discuss the selection of appropriate transformer sizes and ratings. Selecting the correct transformer size is crucial for efficient and reliable operation. An undersized transformer can overheat and fail, while an oversized transformer can operate inefficiently and waste energy. To determine the appropriate transformer size, you need to calculate the total load that the transformer will supply. This includes the connected load, the demand factor, and the diversity factor. The connected load is the total power consumption of all of the equipment that will be connected to the transformer. The demand factor is the ratio of the maximum demand to the connected load. The diversity factor is the ratio of the sum of the individual maximum demands to the maximum demand of the entire system. Once you have calculated the total load, you need to select a transformer with a kVA rating that is greater than or equal to the total load. It is generally recommended to select a transformer with a kVA rating that is 125% of the total load to provide some margin for future growth. Also, consider the transformer's voltage rating. The transformer's primary voltage rating should match the voltage of the power source, and the transformer's secondary voltage rating should match the voltage of the equipment that will be connected to the transformer. Consider the transformer's impedance. The transformer's impedance can affect the voltage regulation and short-circuit current of the system. A higher impedance transformer will have better voltage regulation but will also have a lower short-circuit current. Consult with a qualified engineer to determine the appropriate transformer size and ratings for your application. This will help ensure that the transformer operates efficiently and reliably. Remember that proper transformer sizing is essential for minimizing energy losses and preventing equipment failures. This is a critical aspect of electrical system design.